Hello. Welcome to Design of RC Structural Elements class, that is 18 CV 53. So, Module 1. So, deflection and cranking part comes under Module 1. See, whenever we design a structure under limit state design procedure, so we have to design the structure for two limit states mainly. One is the limit state of collapse and the second is the limit state of serviceability. So, under limit state of collapse, we have got limit state of flexure, then limit state of shear, torsion, etc. Similarly, for the limit state of serviceability, that is limit state of deflection, limit state of cracking, temperature, durability, fire resistance, etc. Those things come under serviceability limit state. So, strength limit state or collapse limit state and serviceability limit state. Any structure not only has to be safe, it should also be serviceable and finally it should be economical. So, what is serviceability? So, actually deflection and cracking comes under serviceability limit state. So, deflection and cracking, every structure is bound to deflect under different loads and different combinations of loads. Similarly, and depending on the load and depending on the way we design, there may be some cracks, and of course, if at all the cracks appear, we have to keep those cracks within certain limits as per the codal recommendation. So, in this class, to start with, I am going to concentrate on limit state of deflection. So, as I said, every structure or every structural element, mainly beam and slabs, are bound to deflect, and our job is to keep those deflection within certain limits as per the codal recommendation. If you go to section 23.2 or class 23.2 of IS 456-2000, so it gives a set of recommendations on how to control deflections. And whenever we calculate deflection, total deflection, those deflections should be within certain limits so that any partition walls should not develop cracks, because if the deflection exceeds certain limits, and also it should not cause ponding for the slabs. Ponding is nothing but because of excessive deflection. So, if we pour some water on the floor, it gets collected at the middle. That is ponding, and we should avoid it, and otherwise it is not going to serve the purpose for which the structure has been constructed. So, when it comes to the limit state of deflection or simply deflection, which I am going to cover in this class. So, we have two types of deflections. One is short term deflection and the other is long term deflection. So, what is short term deflection? If you subject a structural element to load, external load, immediately after it is made to use. So, whatever the deflection takes place due to elastic properties of the material, that is immediate deflection. That happens due to self weight of that structural element, and also it happens due to any additional dead load on that structure, and also it happens due to live load. So, those are elastic deflections, and long term deflections are nothing but the deflections happen due to shrinkage of concrete, then shrinkage of concrete, temperature variation, and also creep of concrete. Those are all long term deflection. So, again, total deflection is short term deflection and long term deflection. So, total deflection is normally 2 to 3 times the immediate or short term deflection. To start with, let me take the deflection part. So, that is AT equal to total deflection. One is AI, that is immediate deflection, plus ALT, that is the long term deflection. and short term deflection plus long term deflection can further be divided into ACS plus ACC plus ATP. That is deflection due to shrinkage, deflection due to cracking, and the deflection due to temperature change. So in this class, so we don't deal with this. We are going to deal with only these two because this is not so much significant under normal temperature. So we are going to find out what is the total deflection of a structural element, so under these three cases. Okay, and where here AT equal to total deflection then deflection due to shrinkage of concrete and deflection due to creep of concrete. Okay, and here AI is short term or immediate. Immediate deflection, and ALT is long term deflection. And as I said, deflection should not exceed certain limits, and we have to keep the deflection as minimum as possible. So how do we keep the deflection as minimum as possible? So as per the codal recommendation, we have to maintain certain L by D ratio. What is the L by D ratio? L is nothing but the span of the structural elements and D is the effective depth. So we have to maintain those values within certain limits so that deflection is under control. If you go to page number 37 under 23.2, so I am going to read out. So the deflection of a structure or part thereof shall not adversely affect the appearance or efficiency of the structure or finished partitions. The deflection shall generally be limited to the following. So the final deflection due to all loads including the effect of temperature, creep and shrinkage and measured from the as cast level of the supports of floors, roofs and all other horizontal members should not normally exceed span divided by 250. What it means is the final deflection, that is the immediate deflection plus long term deflection, should not exceed the final deflection. I write final deflection should not exceed or at most equal to span divided by 250. Okay, that is, it should not be greater than span divided by 250. Again, if you go to the next one, it says the deflection including the effects of temperature, creep and shrinkage occurring after erection of partitions and the application of finishes should not normally exceed span divided by 350 or 20 mm, whichever is less. What that means, this is the deflection due to temperature plus creep plus shrinkage should not be greater than span divided by 350. See, what exactly it means is total deflection should not exceed this much. What is the total deflection? As I said, the total deflection is the short term deflection and the long term deflection. it should not exceed this. And when it comes to the long term deflection, then the long term deflection should not exceed span divided by 350. So whenever we check for deflection, we have to check for two conditions. One is for long term deflection. When we calculate deflection, immediate or short term deflection, one part we are going to calculate, and the next one is long term deflection. So take that long term deflection calculated separately and make sure that value does not exceed this. Afterwards, we have to go for another check. So what is the other check? This is the other check. Add both short term and long term deflections, add them together and make sure that value is, that is the final deflection is not greater than span divided by 250. So that's what the code recommends. Next, when it comes to the control of deflection, so we have to follow certain guidelines given by the code. So when we follow those guidelines, the deflection will be under control. That means generally these conditions are satisfied. So what are the codal recommendations? So codal recommendations under class 23.2.1, it says the vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratios are not greater than the values obtained as below. So it is generally assumed to be satisfied. That means in majority of the cases, if we follow, for example, for cantilever, basic values of span to effective depth ratios for spans up to 10 meter, it is 7. For cantilever, 7. Okay. So similarly, for simply supported, it is 20. For continuous, it is 26. If the span of any structural elements crosses 10 meter, then we have to give certain corrections as per the codal recommendation. Okay. This is the way we are going to control the deflection, and in some structures, when we cannot follow this, or we somehow for practical reasons, if we cannot stick to these conditions of L by D ratio, then go ahead and provide whatever the situation demands for the design. In such cases, when you are checking for the deflection, you have to check for the actual deflection using all the complex formula given in the code. So once you calculate those values, make sure those values are satisfying these two conditions. So next what I do is, how do we reduce the deflection? So the deflection can be reduced by different ways. That is by decreasing the depth of the section. When you decrease the depth of the section, what happens to the moment of inertia? Moment of inertia is going to increase. So once you increase the moment of inertia, if you go to any formula to calculate the deflection, moment of inertia comes in the denominator. So once the moment of inertia increases, the deflection reduces. So by increasing the depth, we can reduce the deflection significantly. Not only that, we can increase the deflection by widening the width of the structural member. Say for example, if I take a beam, if you increase the width, yes, we can reduce the deflection as well. So by using rich concrete, we can reduce the deflection, and also by providing camber for the beam or for the slab at the middle within certain limits. Once you provide the camber, so what happens under self-weight and under external load, so the slab or the beam will try to flatten. That way we can reduce the deflection as well. And also by making use of the T-section. Of course, when we are casting a beam, what we do is we normally cast the beam, that is a rectangular beam, along with the floor. So that beam serves as a T-beam. So by adopting T-beam design, we can definitely reduce the deflections. Let us take up an example, a cantilever of 3.5 meter span is 300 millimeter wide, 300 millimeter wide and 600 millimeter deep. It is subjected to a maximum bending moment of 125 kilonewton meter due to uniformly distributed service loads, uniformly distributed service loads, of which 50% moment is due to permanent loads. Due to permanent loads. The beam is reinforced with 4 bars of 20 mm dia at an effective cover (50 mm) in the tension zone. In the tension zone. Check the beam for deflection. Check the beam for deflection. See, let me read out the problem. A cantilever beam of 3.5 meter span is 300 millimeter wide and 600 millimeter deep. That is 300 millimeter wide and 600 millimeter deep. Okay, this is B, this is capital T. It is subjected to a maximum bending moment of 125 kilonewton. So, due to uniformly distributed service loads, so whenever we calculate deflection, we always make use of the load of service, that is the service load, not the ultimate load or the design load. Okay? And due to that, due to the service load, the moment we are going to get is 125 kilonewton meter, of which 50% moment is due to permanent loads. So total service moment is 125 kilonewton meter, out of which 50%, that is 62.5 kilonewton meter, is the moment due to permanent loads. So the beam is reinforced with 4 bars of 20 mm diameter at an effective cover of 50 mm in the tension zone. Check the beam for deflection. See, because this is cantilever, tension happens at the top. That's why we are going to provide reinforcement at the top, 50 mm, and it has 4 bars of 20 mm diameter, and we need to calculate the total deflection due to the load. So let me write down what are the things given in the problem. So cantilever length L equal to 3.5 meter, breadth B equal to 300 millimeter, and total depth D equal to 600 millimeter. Area of tension steel AST equal to 4 multiplied by pi by 4, 20 square, that is equal to 1256.64 millimeter square, and MC, that is the total maximum bending moment due to service load, is 125 kilonewton meter, or 125 into 10 to the power of 6 Newton millimeter. And the the concrete we are going to make use of is 20 Newton per millimeter square, and the steel we are going to use is 415 Newton per millimeter square. So as we discussed, total deflection AT equal to AI plus a long term deflection, that is equal to AI plus deflection due to creep and deflection due to shrinkage. So I am going to call this equation 1. So I am going to find out one item at a time, and once I get all those individual deflections, I am going to put those individual deflections in this equation, and finally I am going to get what is the total deflection. Let me start with AI value, that is the short term deflection or immediate deflection. To calculate, short term deflection AI. So we have the formula for a cantilever. Short term deflection AI equal to WL to the power of 4 E, and I is effective with 8 here. So this is the formula to calculate the deflection for a cantilever beam under uniformly distributed load. So what I do is I am going to split this formula this way, and I am left with L square divided by 4 AC I effective. So what is WL square by 2? WL square is the maximum bending moment at the support due to the service load. So that is equal to MC L square divided by 4 EC I effective. Of course, here MC is known because that is given already. MC is how much? That is 125 multiplied by 10 to the power of 6 Newton millimeter. So L is known, that is the length of the cantilever, which is 3.5 meter, that is equal to 3500 millimeter. EC is the Young's modulus of concrete, and IEFF is the effective moment of inertia of the section which we need to calculate. Here let us find out each item at a time. MC is known, L is known. Let us find out what is EC. Now EC equal to 5000 FCK as given in the code. That is 5000 and FCK is 20 square root of 20, that is equal to 22361 Newton per millimeter square. That is the Young's modulus of concrete. Now we will find out what is IEF. IEF formula we are going to get under annexure C, page 88 of the code book, and IEFF, that is the effective moment of inertia, is IR divided by 1.2 minus MT divided by M Z divided by D 1 minus X by D BW by B. So here what is IR? So IR is the moment of inertia of the cracked section, and what is MT? MT is nothing but cracking moment, which we are going to find out using the bending equation in strength of materials. So what is MT? MT is nothing but MC value here, that is 125 multiplied by 10 to the power of 6 Newton millimeter, and X is the depth of the neutral axis from the compression edge, and D is the effective depth, BW by B. BW is the width of the web and B is the width of the flange. If you are finding out the deflection of a T-beam, so whatever T-beam width we are going to find out using the codal recommendation, so we have to put here. But for a rectangular section, so BW and B are one and the same, so this value is going to be 1. So let us take up IR, that is, let me start from here to find out what is IR. And of course, I forgot one step, IR should be less than equal to I effective, and that should be less than equal to I gross. Okay. So this is the moment of inertia of the cracked section, this is the moment of inertia, that is the effective moment of inertia and also this is the moment of inertia of the gross section. And we have to make sure that this value which we are going to calculate lies between this and this. So what if this value goes below IR? Then we have to take this value equal to IR. If this value goes above IGR, we are going to take IGR as I effective. So that is the way we are going to go. Let us find out what is IR first to start with. That is moment of inertia of the cracked section. IR. So before starting the moment of inertia of the cracked section, first I am going to find out what is the modular ratio. So modular ratio M equal to Young's modulus of steel divided by Young's modulus of concrete. So Young's modulus of steel is 2 multiplied by 10 to the power of 5, and the Young's modulus of concrete is 22,361 Newton per millimeter square, which we calculated just now. So after doing the calculation, we are going to get the value of modular ratio M equal to 8.94. So to find out the moment of inertia of the cracked section, what we do is, first we are going to find out what is the depth of the neutral axis. This is the depth of the neutral axis. Because this is cantilever, so anything below the neutral axis is going to be subjected to compression. If x is the depth of the neutral axis from the compression edge, then I am going to call this as D. D is the total depth minus the effective cover, so that is equal to 550 millimeter, and this is 300 millimeter width. Okay. So before finding out the depth of the neutral axis, what we need to do is we need to convert this steel area into equivalent concrete area. So if I do that, so what happens is, same section, this is X, okay, and I am converting this steel into equivalent concrete area. That will be like this. So this area will be equal to M times AST, and of course this is the effective depth, 550 millimeter, and this is 300 millimeter, this is B. And how to find out the depth of the neutral axis? So depth of the neutral axis can be calculated by equating the moment of area of the concrete about this axis, okay, on both sections, and equating those two moments. That is nothing but to find out X by equating moments of areas in both tension and compression zone about the neutral axis. So that is moment of the compression area of concrete about the neutral axis is given by M into AST, that is the equivalent concrete area, and D minus X is the distance of the centroid of the equivalent concrete area from the neutral axis. That should be equated to, so B times X is the area of the compression zone and the distance of the centroid of the compression zone is X by 2 from the neutral axis. So here B is 300, X square by 2. I am going to take this side, MAST. So MAST is plus 8.94 into 1256.4 and X minus 8.94 into 1256.64 into D is 550. So finally this will reduce to X square plus 74.90X minus 41192.66, that is equal to 0. So that is therefore X equal to 168.94 millimeter. That is the depth of the neutral axis. So that is X equal to 168.94 millimeter. Now let us find out what is the moment of inertia of the cracked section. So moment of inertia of the cracked section is IR. After all, by definition of the moment of inertia, it is the second moment of the area. So I am going to take the moment of inertia of this about this neutral axis, that is MAST, and the distance is D minus X square, and the moment of inertia of this compression zone is given by B D cube. B is 300, D is X cube by 3. This is a rectangle, and the moment of inertia of this rectangular portion about its own centroidal axis is BDQ by 12. If we take the moment of inertia of the same rectangle about the base, it is going to be BDQ by 3. Here D equal to X, that is the depth of the neutral axis. So that is BX cube by 3. So I am going to substitute all the values, that is 8.94 into AST is 1256.64 and D is 550 minus X is 168.94 plus 300 into 168.94 cube by 3. So that is IR equal to 21.13 into 10 to the power of 8 millimeter to the power of 4. That is the moment of inertia of the cracked section. Short term deflection. Okay. Okay. Next, we will find out what is cracking moment. So, cracking moment, I am going to make use of the formula given in the code, that is nothing but the bending equation of strength of materials. So, next, to calculate cracking moment, so that is M R equal to FCR IGR divided by YT. So, that is the formula for calculating the cracking moment, that is given in C 2.1, that is under annexure C on page 88 of the code book. So, FCR, what is FCR? That is the modulus of rupture of concrete. That is modulus of rupture of concrete, FCR equal to 0.7 square root of FCK, that is equal to 0.7 square root of 20, that is equal to that is equal to 3.13 Newton per millimeter square. Then what is IGR? That is the moment of inertia of the gross section. That is IGR equal to 300 multiplied by 600 cube by 12, that is equal to 54 into 10 to the power of 8 millimeter to the power of 4. Next, what is YT? YT is the distance of the extreme fiber from the neutral axis. So, what is the distance of the extreme fiber from the neutral axis? It is going to be half the depth of the section. So, YT equal to so 600 by 2, that is equal to 300 millimeter. So, we know all the values. We can find out what is the cracking moment MR. Therefore, MR equal to FCR, that is 3.13 into IGR 54 into 10 to the power of 8 divided by YT is 300 millimeter. So, the cracking moment is 56.34 into 10 to the power of 8 millimeter to the power of 4. That is the value of the cracking moment. Next comes, if you look at the equation of IEFF, that is the formula of IEFF. So, there is one term called Z. So, Z is the lever arm. So, lever arm Z equal to from the centroid of the tension steel to the centroid of the compression zone. So, here we are going to assume the linear variation of stress in concrete. As a result, the resulting force, compressive force, is going to be located at a distance of x by 3 from the edge of the compression zone. So, lever arm is given by D minus x by 3, that is equal to 550, and the value of x is 168.94 by 3. That is equal to 493.7 millimeter is the lever arm. Now, by substituting all the values, now if you go to that equation given in the code, IEFF equal to I R divided by 1.2 etc. So, we know all the values here. So, once we know all the values, substitute the values and get the value of I effective. So, I effective by substituting all the values in the above equation, we get I effective equal to 21.13 into 10 to the power of 8 divided by 1.2 minus 56.34 into 10 to the power of 6 divided by 125 into 10 to the power of 6 and 493.7 divided by 550 multiplied by 1 minus 168.94 divided by, so let me substitute x divided by 550 multiplied by BW divided by B in this case for a 1 for a rectangle section. So, I effective is 22.97 into 10 to the power of 8 millimeter to the power of 4. In this equation, just make sure moment of inertia of the cracked section IR is less than equal to IEFF and that is less than equal to I gross. Okay. So, in this case, yes, it is true. If you look here, so IR is less than this value and this value is less than I gross, that is IGR, which is here. Therefore, here IR is less than I effective and I effective is less than I gross. Therefore, okay. Now, we calculated the moment of inertia. Next, we need to calculate what is the short term deflection. Now, by substituting all the values in equation 1, we get the short term deflection the short term deflection AI equal to 125 into 10 to the power of 6 multiplied by 3500 square divided by 4 into 22361 22.97 into 10 to the power of 8. So, after simplification, we are going to get the short term deflection. Therefore, short term deflection. Or elastic deflection equal to 7.45 millimeter. That is, next we are going to continue with the deflection due to shrinkage. Thank you.